Friends, in this video we're gonna talk about Schmitt trigger and we will understand what is this Schmitt trigger and what is the purpose of using Schmitt trigger in electrical and electronic devices and how it is designed. First, let's look what is comparator. A comparator is a device used to compare two voltage levels. The problem with the comparator is that if the input signal is noisy, in that case our output will get affected and will not get the desired output. Let's say we have one comparator where we have applied two input voltages V1 and V2. Let us assume that V1 is the input signal and V2 is the reference signal, and assume these signals are ideal signals. In the case where V1 is greater than V2, we should say that V output is constant high voltage. But if the input V1 signal is noisy, in that case it is possible that it can affect our output voltage. So let's say V1 signal looks like this because of noise in it. You can observe this that V1 crosses V2 over two locations. During this time period, the signal V1 is less than V2. For this duration, we will have a low voltage. So because of noise, you can see there is a transition in the output voltage, or we can say that output will get affected because of noise in the input signal, and you can say that the comparator is immune to the noise, or because of that it can affect our output. Now this kind of problem can be solved using Schmitt trigger. Now, a Schmitt trigger is a comparator circuit with hysteresis implemented by applying positive feedback to the non-inverting input of a comparator or a differential amplifier. This is the symbol of Schmitt trigger, and this is the implementation circuit of Schmitt trigger using op amps. A Schmitt trigger circuit is an active circuit. There are two types of Schmitt triggers: inverting Schmitt trigger, non-inverting Schmitt trigger. Schmitt trigger can be implemented by using op amps, transistors and IC 555 timers. First, let's see the circuit of Schmitt trigger using 555 timer. The circuit diagram is this, and the circuit can be built using the basic electronical components, but IC 555 timer is an essential component in this circuit. Both pins 4 and 8 are connected to VCC supply, and the two pins 2 and 6 are shorted, and the input is mutually given to these pins with the help of a capacitor. The mutual point of the two pins can be supplied with an external bias voltage, that is VCC by 2, using the voltage divider rule that can be formed by two resistors, namely R1 and R2. The output keeps its value while the input is among the true threshold values, which is called hysteresis. This circuit can perform like a memory element. The threshold values are 2 by 3 VCC and 1 by 3 VCC. The superior comparator towers at the 2 by 3 VCC, while the minor comparator towers at the supply of 1 by 3 VCC. The key voltage is contrast with the true threshold values using individual comparators. The flip-flop is arranged or rearranged. Consequently, the output will be high or low depending on. Next, the Schmitt trigger using a transistor. This is the circuit using transistor. The following circuit can be built with basic components, but two transistors are essential components of this circuit. When the input Vin is 0 volts, then the transistor T1 will not conduct, whereas T2 will conductor will conduct due to the V reference with the voltage of 0.98. At node B, the circuit will be treated as a at node B, the circuit will be treated as a voltage divider to calculate the voltage at VA and A and B. The therefore Therefore, when we increase the input voltage V in, the transistor T1 can cross, the transistor will conduct. And this is the reason to drop the base terminal voltage of the transistor T2. When the transistor T2 is not conducting longer, then the output voltage will increase. Subsequently, the V in at the transistor base terminal will be refused and it will deactivate the transistor, as the transistor base terminal voltage will be above 0.7 of its emitter terminal. In this case also we get two threshold voltages. Now we know that Schmitt trigger has two threshold voltages. One is the upper threshold voltage, that is for low to high transition, and the second one is lower threshold voltage, that is from high to low transition. Now let's see how this Schmitt trigger circuit works. Here, let's say that red line represents the input signal, and there are two voltages, lower and upper threshold voltages. Now let's assume that the initial voltage across the Schmitt trigger is 0. As you see here, the initial input signal is 0 and gradually increasing. So the output of the Schmitt trigger will remain low at, at the point the input signal crosses the upper threshold voltage. Up to that point our output remains low. After that point our output signal will remain high. If you observe here, once the input signal crosses the upper threshold, then after it deviates around this upper threshold voltage, but then also our output signal will remain high. It will go low voltage only when our input signal goes below the lower threshold voltage, and so at this point once again our output will become low, and it will remain low until the point the input signal crosses the upper threshold voltage. So again at this point our output will become high, and this will remain high after this point. So you can see over here, even if our input signal will not be varies around the upper and the lower threshold values, our output will not be changed and it remains constant. So we can say that the Schmitt trigger provides the noise immunity over this point. The difference between the upper and the lower threshold is known as hysteresis voltage of the Schmitt trigger. So basically this hysteresis voltage defines the noise immunity of a given Schmitt trigger. So if you observe in this example, there are four parameters which are required to define the Schmitt trigger. The first two are low and high output values of the Schmitt trigger, and remaining two are the upper and the lower threshold values, are which will decide the triggering instance for the Schmitt trigger. These are the four parameters defines the characteristics of a Schmitt trigger. The characteristics of the symmetric trigger can be graphically represented by transfer characteristic curve. Here the x-axis we have input voltage, and the y-axis we have the output voltage. Now for the given example, the schematic the transfer characteristics of the Schmitt trigger. Now if our input signal is less than the upper threshold value, the trigger in this case, our schemic trigger in this case, our output will remain low, and as soon as it crosses the upper threshold level, then our in output will become high. And if the input signal goes beyond the upper threshold, then also our output will remain high. Now suppose if our input signal start reducing, and then also our output will remain high, and it will remain high until the point our input signal goes below the lower threshold voltage level. So as soon as your input signal goes below this lower threshold voltage, then again your output will become low voltage, and in our input signal goes below the lower threshold, then also our voltage remains low. So this is how a schematic trigger can be representing using this transfer characteristics. The transfer characteristic is also known as the hysteresis curve for the schematic trigger. Now here we have the output voltage levels VH and VL equal and opposite in polarity, so that the curve is symmetric with respect to y-axis. And by providing the reference voltage as an input to this schematic, we can shift this curve to either right or left hand side. For the schematic trigger, which we this kind of transfer characteristic curve is known as non-inverting schematic trigger, because here once our input signal crosses this upper threshold level, then our output will become high, and when our input signal is less than the threshold, then our at this time our output will become. So we can say this transfer characteristics curve is a curve for non-inverting schematic trigger. So similarly we can have a hysteresis curve for inverting schematic trigger. So in case of this inverting schematic trigger, whenever our input signal is less than lower threshold value, at that time our output will remain high, and once it crosses the upper threshold value, our output will become low, and if goes beyond the upper threshold value, our output will remain low, and and will remain low. And suppose if our input signal start reducing, and then also our output signal will remain low, and it will remain low until the point the input signal crosses the lower threshold value. See, once this input signal crosses the lower threshold value, once again our output will become high, and this is the transfer characteristic curve of an inverting schematic trigger. And this curve can be shifted either right or left by providing the external reference voltage as the input to this inverting schematic trigger. So this is the symbol of the inverting schematic trigger. So if you observe here inside the in here, the hysteresis curve inside this triangle is the hysteresis curve of a non-inverting schematic trigger with a notch. It can also be represented by hysteresis curve of inverting schematic trigger. Now let's design an inverting schematic trigger using op amps. Now here the input is applied at the inverting terminal, and a positive feedback from the output to the input side. Now let's understand how this circuit will work as an inverting schematic trigger. Now let us assume the voltage at this inverting terminal as V plus, this as V plus. If when V in is greater than V in is greater than V plus, then at that time our output will be become low voltage. Whenever V in is less than V plus, at that time our output will be high. Now in case of non-inverting schematic trigger, this is a symbol of non-inverting schematic trigger, where inside the triangle there is this hysteresis curve of non-inverting schematic trigger. Now we'll see how to design a circuit of non-inverting schematic trigger using op amps. So here we have applied the input at the non-inverting terminal, and there is a positive feedback from the output to the input side. And now let's understand how this circuit will act as a non-inverting. So once again assume the voltage at this node is equal to V plus, and here if you observe, the inverting terminal is at ground potential. So whenever V plus is greater than 0, in that case our output of the op amp will be high, and whenever the V plus is less than 0, in that case our output will be low. Now let's see the applications of Schmitt trigger, analog to digital. The Schmitt trigger is effectively a 1-bit analog to digital converter when the signal reaches a given level in switches from its low to high state. This is a analog to digital converter, and this is a graphical representation how it looks. Next, the level detection. Another application is level detection. The Schmitt trigger circuit is able to provide level detection. When undertaking this application, it is necessary that the hysteresis voltage is taken into account so that the circuit switches on the required voltage. Line inspection. When running a data line that may have been picked up noise into a logic gate, it is necessary to ensure that the logic output level is only changed as the data changed and not as a result of a suspicious noise that may have been picked up. Using a Schmitt trigger boldly enables the peak-to-peak noise to reach the level of the hysteresis before suspicious triggering may occur. Yes, thank you. That's all. Here we have learned about Schmitt trigger and its applications. So thank you for watching this video.